Hello. In this video, I'd like to talk about the concepts of heat and heat capacity, and more specifically, specific heat capacity, and what they are and how they relate. First of all, let me just mention very briefly the difference between temperature and heat. The heat is basically energy that is transferred from a hotter object to a colder object, and temperature is kind of a measure of the kinetic energy of some particles. So if I have two objects, and this is the hot, it's got a high temperature, and this is another object over here, and this has a cold temperature. So they both have some temperature. If you could look at them, the particles are vibrating and moving. There's freedom of movement here. The particles are vibrating around. The particles are vibrating here. If we look at the average kinetic energy or motion of these particles, it's going to be greater than these, and therefore its temperature is higher. Now, if I bring this one in contact with this one, these faster moving particles will give energy by striking these, causing them to move faster. So then these particles, their speed will go up, and therefore their temperature go up, because as their kinetic energy rises, their temperature rises. Well, what we have done is we have transferred some energy from here to here, and that is what we call heat, and that's Q. So there is a difference. Q is measured in joules, J-O-U-L-E-S, named after James Joule, who came up with a lot of the ideas and some first law of thermochemistry and so forth. Temperature then is of this individual system the average kinetic energy of the particles. Now, I do say average. Not every particle in here is moving at exactly the same speed. This is kind of a distribution, and it would certainly be a distribution. You're going to have some moving very fast, some moving kind of slow, a whole lot in the middle, and your average, of course, would be somewhere in the middle of all this. So that's a little bit about the idea there. Now, what I want to talk about next is how hard is it to heat something up. If I put a little energy into some things, their temperature goes up real quickly. Their particles move faster and they jump up very, very fast. If I put a lot of energy or some energy into something, temperature doesn't move at all. That's the idea of specific heat capacity. Specific heat capacity is the amount of joules of energy needed to take 1 gram of something and raise its temperature 1 degree C. I have some specific heats listed here. Specific heats are abbreviated with a C, or the way I learned it, it was C sub P, and you'll see both. I'll probably revert to C sub P. That's what I used over here in my equation, just because that's what I grew up with. But again, C sub P is the specific heat, and that is the number of joules per gram degree C. So how many joules of energy do I need to put into each gram to get its temperature to go up 1 degree C? And you'll notice there's quite a variety. Something like selenium, it only takes approximately a third of a joule to take 1 gram and raise its temperature by 1 degree C, as opposed to water, which famously has a very, very high specific heat. It's 4.184 joules to get 1 gram of water to go up 1 degree C. So it takes a while for for its temperature to rise, because you have to put a lot of energy, a lot of heat into it before the temperature will go up. Whereas something like xenon down here, 0.16, you don't have to put much energy at all into that before its temperature will rise. Okay, so how do we relate all this? How do we relate temperature and heat and specific heat and so forth? There's a very common formula. It's used in a lot of chemistry classes quite a bit. And the formula is simply Q is equal to M delta T Cp. And what these are is, this is the heat, and so this is always measured in joules, which I abbreviate with a J there. This is your mass. Okay, and I'm using a lowercase m to distinguish it from molarity or some other things we'll use in chemistry. But that is your mass, and that is in grams, because notice that my specific heat is in grams. My delta T, and again, delta that's a Greek letter delta. It basically means change in temperature. And whenever you use that, it's always the final temperature minus the initial. So you're going to see in some problems you're not actually given the change in temperature, but you're given the initial temperature and the final temperature, and then you have to calculate out the delta T. To do that, you always want to take the ending temperature minus the initial. And then this one is, as I mentioned over here, the specific heat. And that heat, my E looked a little funny there, specific heat, and that is measured in joules per gram degree C. Now, interestingly, notice in my formula, if I have joules per gram degree C and I multiply that by grams in degrees C, that cancels and my answer would be in joules, which is what Q is in. So if I take the mass times the delta T times the specific heat, the joules and degrees C's will cancel and my final units will be, or I'm sorry, my grams and degrees C will cancel and my final answer will be in joules. So that's kind of how this works, and now what I'd like to do is just do a few problems and show you how these work. So in my first problem, which I'll kind of do right over here on the side, let me pick a different color here. Okay, it says how many grams of a sample of calcium carbide will be required if, as it cools from 74.2 to 11.5, it releases this much energy. And this is heat. The CP is given to you here. Okay. In this kind of a problem, they want grams. So basically that means I'm trying to solve for mass. So if you rearrange our equation, basically you'd want to divide both sides by delta T CP. That will cancel on this side. So on the other side, you're going to have Q over my delta T times my CP. So then we plug in, okay, how much heat was released? Well, the heat that was released here was 2680 or 2680. By convention, whenever they say it was released or given off, it's considered to be negative. You know, if I give away $1,000, my net value has gone down by 1,000. I've released that, so my value has gone down by 1,000. So it's the same thing here. If you're going to release heat, it's negative 2680, and that is in joules. Q is always in joules, divided by my delta T. Well, my delta T is 74.2 and 11.5, so I have to take the final 11.5 minus the initial 74.2, and I did that ahead of time, and I think it came out to negative 62.7. So hopefully I did not make a mistake there, times the CP, and again, that is given to me in the problem as 1.00. And again, if you do the units here, this would be degrees C, and this would be joules per gram degree C. So what will happen is if you go through all this, you'll see the joules will cancel, the degree C's will cancel, I'll be left with grams, which is actually what I want. And when you do the math here, I got, again, this is negative, so it all cancels out, which makes sense. You shouldn't get a positive mass, or a negative mass, I should say. To 3 digits, I got negative, be positive, my apologies, 42.7. 42.7 grams. Okay, so that's how I would do that problem. Now again, please, just a few things to note here. When they ask, a lot of folks get confused about heat versus specific heat. There is a very distinct difference. Whenever they give you heat, that's your Q. Specific heat is always the CP number. Okay, so let me do this next problem because we're going to solve for something a little bit different here. So let me pick a different color so it's kind of clear which problem I'm solving. How much heat is required to raise the temperature of this many grams, this temperature change, and this specific heat? So notice here they're asking me for heat, so I'm really solving for Q. So the nice thing is I don't have to do any rearranging. I'm solving for Q. That will be equal to the M times the delta T times the CP. So I just plug in these variables. What is my mass in this problem? It is 789 grams times my delta T, so I take the 82.7 minus 25.0. Let me look here. I did that a moment ago as well, and I got 57.7. 57.7 degrees C times the specific heat, which is given to me as 2.05, and that is joules per gram degrees C. And again, notice as far as my units, my grams and degrees C will cancel, so my answer will be in joules, which would be correct, and that will give me the correct answer. And when I do this rounded to 3 digits, because that's pretty much what I have across the board here, I get 93,300 joules of energy. So that's how much energy would come out, or be absorbed, in this case. And again, notice it is positive. The heat, I'm putting energy into this acetic acid, which is causing its temperature to go up. So it makes sense if it was a positive sort of a heat change. Then for this last problem, you know what, I actually haven't done black yet, so let me do black. What is the specific heat of aluminum if you have this mass, this temperature, and this heat? So notice in this particular case, now I'm asked for specific heat. So please note that difference. Here I'm asked for heat, so that's Q that I was solving for. Here I'm asked for specific heat, so in that case I'm going to solve for CP. And again, CP, or specific heat, or C. To get that, to isolate that, I would divide both sides by M and delta T. So that would be equal to my Q over my M delta T. So what is my Q? Well, they tell me that 207 joules is added. So I put that into this. My mass, I'm told, is 28.4 grams. And my delta T, actually, they just gave it to me. I didn't have to do any subtraction. They told me it changed by 8.1 degrees C. And so I take, and when I do my math, notice my units will be in joules over gram degrees C. Nothing cancels, and those are my units for specific heat, so that kind of lets me know I set it up properly. And when I did this before, I got 0.90, and that is actually the specific heat of aluminum. So I hope this helps you a little bit. It shows you how, first of all, what the difference between temperature and heat, which is an important concept, and the difference between like heat and specific heat in the problem, how you go through and how you solve these problems.